Hi, everybody. Sorry I'm out today. I'm at my daughter's school doing a science experiment day with her and her classmates. I had to help her teachers out. So instead of me being here to teach you the lesson, this video will. I know you're very happy about that. All right, guys, here's what we need to do. If you haven't already, you should have your notepad at 13 out, nuclear chemistry, and you should have it open to page 8. Page 8 and note packet 13, nuclear chemistry. All right, everyone, we have two goals for today. We're going to talk about some radioisotopes and their uses in our modern society. Unfortunately, you have to memorize these isotopes and their uses for the regions. And then also we're going to start talking about artificial transmutation today. Next class, we'll talk more specifically about fission and fusion, but we'll at least get the basics down for what happens during artificial transmutation. All right, I'm ready to go. So if you haven't, notepad at 13, page 8 is where we are at. All right, so there we go. All right, here we go. All right, so there's several uses of radioisotopes in our modern society. This is only a partial list. Nuclear power is one of them, but we won't talk about that today. We're going to focus on radiochemical dating, using radioactive isotopes to figure out how old some sample of matter is, medical applications, how radioisotopes are used in medicine, and then also how we use them in our food preservation process. So here we go. Unfortunately, everyone, you just have to memorize these isotopes and their uses. The Regents can ask you about any of them, and I'll try to give you some memory tricks to go along with them, as many as I can think of. All right, so here we go. We're going to go with the two used in radiochemical dating. The first is if you have an organic remains, so the remains of something that was once living. Carbon-14 is used to date organic remains. So basically what happens is scientists dig up some specimen of something that was once living. Everything that's living, for the most part, has carbon in its body at some point in time. Scientists look at the ratio of carbon-14 to nitrogen-14, which is what carbon-14 decays into through beta emission. And based on that ratio of carbon-14 to nitrogen-14, they're able to determine roughly the approximate age of the once living organism. All right, so PB, uranium-238 is used to date non-living things, determine the age of things like rocks and minerals. Basically, if you have some rock that has uranium-238 in it. Uranium-238 decays very slowly over time into lead-206. So scientists can look at the ratios of uranium-238 to lead-206 in some non-living sample, like a rock or a mineral or something like that, and roughly approximate the age of the sample. All right, carbon-14 is used to date the remains of once living things, and then uranium-238, the ratio of that to Pb-206 is used to date non-living things like rocks and minerals. All right, up next, we have medical applications of radioisotopes. So if you are using a radioisotope in some sort of medical test or medical procedure, you're going to want it to have two properties. The first thing is you want it to have a short half-life. And because it has a short half-life, that means that radioisotope will break down quickly. It will decay quickly, and your body will be able to quickly eliminate it. So we want our isotopes used in modern medicine to have short half-lives so that they can be quickly eliminated from our body. It reduces the amount of radiation exposure to the patient and also reduces the chances that patient might receive some cancer or gene mutation risks. All right, these again, they're just memorized. I'm sorry, but that's the way it goes. Here's what we got to know. Iodine. Here, the I in iodine. It's used to diagnose thyroid disorders. So the thyroid is a body organ that is really susceptible to iodine. It really takes it up quickly. So you can inject a patient with iodine 131 and monitor with special cameras their thyroid function during that time. And based on how well the thyroid is able to process that iodine 131, you can tell whether or not there's issues with the thyroid. TC99M, the M is for metastable. This is actually a man-made radioactive isotope. It doesn't occur naturally in the universe anywhere that we know of. TC99M is used in the location of brain tumors. So if you're going to inject a radioisotope into your brain, you probably want it to be as least harmful as possible. TC99M emits gamma radiation, which I know is not great, but it's still better than beta radiation. So TC99M is a radioisotope used in brain scans because although it does suscept your brain to radiation, at least it's gamma and it's not beta, which is potentially more damaging. All right, and last but not least, cobalt-60. Cobalt starts with a C, so does cancer. So that's my memory trick for you. Cobalt-60 is used in cancer therapy. Cobalt-60 emits both beta and gamma radiation, so it's used to target tumors in the human body. Those are both very high energy forms of radiation, and it can destroy the tumor. That's like what chemotherapy is, but unfortunately it can take out other healthy cells as well. All right, there's your three medical isotopes. Iodine, I for thyroid, I and thigh, I don't know. TC99M is for brain tumor location, and cobalt-60 is used in cancer therapy. All right. We also can use radiation to treat our modern produce, our veggies, our fruits, even meats can be irradiated. The point of irradiating our food is to eliminate any mold, bacteria, yeast, any yucky stuff on the food that we don't want on it. And ultimately what that does is it prolongs the food item's shelf life. So your apples last longer, your meat lasts longer. A lot of our food is irradiated before we eat it. Don't worry though, the radiation quickly leaves the food. It's not in there. You're not ingesting it. You're not eating it. It's just basically used to kill like anything on the surface of the food that might make it rot or decay more quickly. All right, there you go. There's your uses of radioisotopes in modern society. Sorry, a lot of it you do have to memorize. All right, moving on. So now we're going to skip. We're going to skip in the notes. We're going to go to page 11. And what we're going to do now is we're going to start talking about artificial transmutation. So like everything we've talked about so far has been natural. We have some natural nucleus that's unstable naturally. It naturally decays by producing some types of products. What we're going to talk about now is artificial transmutation. All right. So basically, if you have artificial transmutation, you have some stable nucleus right here, and you're going to bombard it or hit it with some fast-moving particle. And when you hit that nucleus with some fast-moving particle, it absorbs it, and it artificially causes that stable nucleus to mutate into a nucleus of another atom. So up here on the screen, what we can see is we've got a nitrogen nucleus, which is stable. That fast-moving particle that's bombarding it, that's an alpha particle. That alpha particle is absorbed by that nitrogen nucleus, and as a result, it forces it to transmutate or turn into an oxygen nucleus. We do this for a lot of reasons. Nuclear power is brought about this way. When we're trying to create new elements and particle accelerators, we do this. So there's different ways this is used in our modern society. All right, so what is artificial transmutation? It is the bombardment or hitting the nucleus of a stable element with some type of high energy particle. Neutrons, not neutrons, I'm sorry, but like alpha particles are used. We do use neutrons in our nuclear reactors. That's kind of a talk for another day. We'll talk about how and why that works. Today is not that day. But basically, artificial transmutation occurs when us as humans take some stable nucleus and force transmutation to occur through hitting that nucleus with a very high energy particle. All right, oops, that says two reactants. That says two reactants. I see the image has cut it off. One big difference between a natural and an artificial transmutation is that artificial transmutation reactions have two reactants, two particles before the arrow, one of which is the stable nucleus, the other is the particle you are bombarding it for. Natural transmutation reactions only have one. All right, so for our let's practice here, I don't know why the recording isn't capturing my screenwriting, but you're going to have to kind of follow along. If you wanted to know which ones of these equations represented natural transmutation, well, what you'd have to do is you'd have to look at the number of reactants. So if you'll look, Number 4 there, the uranium transmutating into thorium in the alpha particle. That one only has one substance before the arrow. That's natural. Uranium all by itself, we don't have to hit it with anything, is breaking down or decaying into thorium by emitting an alpha particle. The other choices, 1, 2, and 3, those all represent artificial transmutation because there's 2 particles before the arrow. So one of them is the stable nucleus. The other notation is the particle that we bombard or hit that stable nucleus with. So artificial transmutation reactions always have 2 reactants and 2 products. And natural transmutation, like number 4, always has 1 reactant. And they make 2 products. All right, moving on. So we do a lot of our artificial transmutation reactions in particle accelerators. So particle accelerators are these huge underground tracks, like a racetrack basically, that use very strong electric and magnetic fields to accelerate charged particles to almost the speed of light. So we get these particles moving really fast in particle accelerators. And then what happens is we have some atom or some particle that we want to hit. So we have that atom or particle stationary inside our particle accelerators. And then we get these fast moving particles whizzing around the track. And when the conditions are right, we collide that particle whizzing around the track at like the speed of light, with almost the speed of light, with whatever atom we're holding stationary that we want to bombard it with. They smash together. There's all sorts of particle or detectors inside these particle accelerators, and we're able to tell what's emitted due to that collision. Sometimes we create new atoms this way. Sometimes we find particles we didn't even know existed in the universe. So a lot of modern physics is taking place in particle accelerators. The largest one in the world is called the Large Hadron Collider. It's under areas of France and Switzerland. This is that yellow circle is its like track. It's 17 miles in circumference. So again, these are huge. They have to be big because we use those strong electric and magnetic fields to accelerate the particles in them to nearly the speed of light. All right, so the key with a particle accelerator is they use electric and magnetic fields to accelerate particles, which means that the particles we accelerate in our particle accelerators, they have to have a charge. Charged particles respond to electric and magnetic fields. Particles that are chargeless don't. So we can currently only accelerate charged particles in our particle accelerators. We get them moving super fast, almost the speed of light. And at that speed, at that energy, when we collide these fast-moving particles with the nucleus, they're able to penetrate or enter the nucleus and force a transmutation to occur. All right, so we cannot accelerate particles without a charge in particle accelerators. So we'll talk about how we use neutrons in nuclear reactors, but we can't accelerate a neutron or gamma radiation, really any kind of energy in a particle accelerator. Why? These particles don't have a charge. They will not respond to electric and magnetic fields. All right, that concludes the notes for today. Next time we meet, we're going to talk about 2 specific types of artificial transmutation, fission and fusion, but that's for next class. Thanks, guys.